In this video, we are going to continue our discussion of the dot product. It's going to manifest itself in this new definition. So let's talk about what a vector projection is. A projection is, we think of projections in light, like we project light to create shadows, stuff like that. That actually is going to apply directly here. What we're going to talk about is projecting this vector A here onto the vector B. What that means is it's like thinking about if there's a sun here shining down, right? My beautiful sun, so realistic, shining down, and it creates a shadow like a noon. This is a noon, 12 o'clock, midday sun is projecting down, and it is creating that shadow PR there. Okay, so we have that shadow PR. That is the vector projection, is that vector PR there, is the projection of A on to B. So, a couple things. What we're going to call that vector is this, projection of A onto B. This is equal to the vector PR. Now, we have a different name. If I want the magnitude of that, we call it comp of A onto B. This is actually the magnitude of PR. Okay, so we're going to come up with a way to come up, if I have A and I have B, how can I come up with the projection and then also my magnitude of the projection? So let's start with that this side is actually the magnitude of A, right? And then we call this side, that's right here, that length is the comp of A onto B. All right, so if I use some trig here, I have an x component with the hypotenuse, that is my cosine. So I'm going to say cosine of theta is equal to the comp of A onto B over the magnitude of A. That's just using right triangle trig. I can go ahead and solve for the comp here by multiplying by the magnitude. All right, so we have that. Now we do have the formula for the cosine there, because we have from that last page or video, cosine theta is equal to the dot product of A dot B magnitude of A times the magnitude of B. We have that. So since we have, okay, and I'm just going to replace cosine in my formula there with that. So comp of A onto B, all right, equals the magnitude of A times, and then I'm just going to put that there, A dot B over the magnitude of A times the magnitude of B. And so we have the comps, the A's cancel. I have A dot B over B. Okay, so I'm going to remind ourselves that vectors, so recall that vectors, remember vectors are defined as two things, a direction and a magnitude. So I'm going to write that here, magnitude times a direction. Now, we have a magnitude. The magnitude of my projection is the comp, right? It's the component projection. It's the magnitude of that. So I can actually write my projection of A onto B by saying, okay, I have the magnitude. The magnitude is A dot B over B magnitude. And then that is my magnitude of the projection. And we just need the direction. Well, the direction is in the direction of B, right? That's where this PR lies here. It's on the direction of B. So I need to multiply by direction. Well, I don't want to do B because that changes my the vector. It's going to change the length. So what I'm going to do is multiply by the unit vector of B. So I got B over magnitude of B. All right, we can actually put this together. The projection of B, A, all right, is, okay, we have A dot B. I'm not going to multiply that with this other B because that's a scalar, what I just wrote down. That's a scalar inside, over the magnitude of B squared times B. So this is going to give me my magnitude, kind of my magnitude. It's the scalar portion. The magnitude is actually right here, but it's the scalar portion, and then the B is just in that direction of B. So this finds that projection. This is going to be very important when we're talking in 3 space, and we're going to need to project things down onto the XY axis. We won't be using the formula a whole lot for our applications in Calc 3, but it is used quite a bit in a lot of physics applications. Okay, so there is my formula there, a nice pretty type. Let's find 2 projections here. We're going to project A onto B and B onto A. All right, so I need to find a few things. I'm going to go ahead and do that. I'm going to find U dot V. All right, so we multiply each component. We got -5 plus -1 plus -7. That is a -5, 6, -13. Yep, okay. We also are going to need the magnitude. We're going to need the magnitude of both. I know I put A's and B's here, but I meant U's and V's. So your note should be right. Mine's probably going to be wrong. It is wrong, not probably. There we go. So that's what we're going to do for that one. And then we're going to do the opposite for this one. There we go. All right, so the magnitude of, I need both of them. So magnitude of U is the square root of the squares of each one. So 25, we did this one earlier, 75. The magnitude of V is going to be the square root of 3. Okay, so I just used the formula now. So the projection is equal to U dot V, which is -13, times the vector V. And then it's going to be the magnitude squared, which is going to of V, which is 3. All right, so we could just leave it like that. We could distribute it through. I guess I'll distribute it. We get 13 over 3, -13 over 3, and 13 over 3. That is my projection. If I wanted the component projection, I would just take the magnitude. All right, so now we're going to flip it and see if it changes. So this projection is U dot V. It's still -13 over now U magnitude squared. So it's over 75 and then times U. All right, we can multiply that through. We get -13 over 25, 13 over 75, and then 70 plus 21, 91, -91 over 75. All right, so that's projection. So we can tell right away that we can't flip our projection and get the same thing. This makes sense because thinking about a shadow being projected, we're not guaranteed if we were to think about having like 2 vectors connected, maybe like having different links and putting some wood down that creates an angle and shining sun down on it. If you were to flip the wood over, like the shadow's different. I hope that makes sense. I'm like talking with my hands through a video. But projections, this makes sense. If we were to flip this over, B would definitely, like this is my ground. B definitely is going to be a different vector. It's not right here, but right, it's going to project at a 90-degree angle down, so you can see that it's going to be different if we were to flip that over. Okay, so those are our projections. Pretty useful. Great.